Welcome to today's webinar about tympanograms, which will be an introduction. You will see through this presentation that I really stick closely to the basics, but let's see where we go. My name is Jos Huyne. I am one of the audiologists working at Introacoustics in the Introacoustics Academy. The learning objectives today, I hope to show you how you can measure a tympanogram and also show the history how the tympanometer developed over the years. And then when we have a tympanogram on the screen, there is two ways of making an interpretation. One is by looking at the numbers, the quantitative analysis, and another one is by classifying it according to its shape and where the peak pressure is, which was first developed by Jerger, and that's Jerger's classification. Then I will tell you what the meaning is clinically of different shapes of tympanograms, and we'll have a short discussion about how valuable it is to do tympanometry. There's also a few things that I do not include in this webinar, and I'll better bring it up front. I won't be talking about wideband tympanometry, however, that is very interesting. If you would like to learn more about wideband tympanometry, then after this introduction, I think it would be very useful to go to our internet webpage. If you go to academy.introacoustics.com, then you will find under e-learning some e-learning courses where wideband tympanometry is explained. Another thing that we won't go over is the die-hard tympanometry theory, the theory that you need to build a tympanometer. There is a very good reference if you are interested in the formulas and how everything works with building a tympanometer, and I recommend finding this link on the internet. Okay, let's start. Why do we do tympanometry? That is because we want to learn something about the ear, and we specifically want to learn something about the tympanic membrane and the ossicular chain, which is laying behind it, and the middle ear cavity. So what we do is we put a probe in the ear, we start presenting a sound, and while the sound travels into the ear, we record what remains behind in the ear canal. So the part of the sound that remains behind shows us something about functionality of the middle ear. While we put this probe tone in the ear, we measure what remains in the ear canal, and basically what it tells us is how easy it is for sound, or this particular tone that we use, how easy is it for that tone to pass through the ear. And another word to describe easiness for sound to pass through the ear is compliance. So we will get a compliance measure. Now, the compliance of the ear is depending on quite a few elements. One is the stiffness. So here you see it pictured as a spring, the stiffness of a spring. If you relate that to our middle ear, it's the stiffness of the eardrum and the ossicular chain behind it, how easily it will allow vibrating when we present the sound. Another element is the mass. What you could think of is that if you have to put a bigger mass in motion, then you need more energy than when you are trying to get a smaller mass in motion. And the last element is friction. So you will lose acoustic energy due to friction, and with regards to the middle ear, it's mostly the friction between the last bone of the ossicular chain, the stapes, which is connected to the cochlea. There is friction there, so you might lose some of the acoustic energy. In an adult ear, with the frequency that we use today for doing tympanometry, it is the case that the middle ear is stiffness dominated. It means that the curves that we measure, it looks like we mostly say something about stiffness of the middle ear, and that is why many clinicians have a feeling that a tympanogram is literally showing the flexibility or stiffness of the eardrum and the middle ear. This is not correct. It's approximately correct for adult ears. So let's assume we present a tone into our ear canal and we measure the compliance, and now we have to put that number on a scale. So we have a vertical line where the higher you go on that line, the more compliant or the easier it is for sound to pass into the ear. Now, if you do one measurement, you would get one dot on this line. Now assume I take the probe out of the ear and I put it back into the same ear. and I redo the measurement, and I do that a couple of times, then you would get a couple of dots on the same line. And the question is, how do we compare these dots with each other? Should it not be almost the same, for example? Now, if we also do that on other ears, we take many ears and we do many measurements, then you will see that we get lots of compliance values which we want to compare to each other, and of which it is difficult to say what is normal, what is not normal, and how does this relate to middle ear pathology. Now, what researchers found out in the beginning, or what they thought about, is that it is an important thing to take notice of the ear canal volume that you find between the probe and the tympanic membrane. The total compliance is, amongst others, dependent on the ear canal volume, and the ear canal volume will be different each time you insert the probe. So in the same ear it will be different, but of course across different ears it will also be very different because of the different ear canal sizes. And if we now could do something to take this volume effect out of the measurement, if we would do that, then maybe we would have a measurement where the dots are much more aligned and closer together and better comparable. And there is a way of doing that, and that is by adding pressure. We have to add a pump to the system, and our graph will now get a pressure axis where positive pressure is on the right side and the negative pressure is on the left side. Now we take the same measurement as we had before, so you see the dot on the vertical axis, and now we will start using the pump and we will look at what happens to the compliance when the pressure changes in the ear canal. And basically we are moving the pressure up and we see that our dot goes down. So it becomes more difficult for the sound to get into the system. And actually what happened to the ear canal is that with the air that we pumped into the ear canal, we pushed away the eardrum. And the eardrum is now fixed and stiff, and in a certain way, acoustically, it is as if the rest of the middle ear and the cochlea behind it is not there anymore. This ear canal now functions as a hard-walled cavity, and in a hard-walled cavity, everything acoustically is only dependent on the ear canal volume, which means that the number of compliance that we measured is purely a volume effect. Now, consequently, it also means that what we measured before was, and the difference between this, between the dot at the positive pressure, is the middle ear effect. So now we have a method of separating the volume effect and the middle ear effect. This is actually a good time to introduce the unit that we use for compliance. And right now I plotted on the graph ohm, which is not the unit for compliance, but many people recognize it as the unit for impedance. And impedance means how difficult it is for something to, in this case, how difficult it is for sound to pass into the ear. And compliance is exactly the opposite. It's how easy it is for sound to pass into the ear. And that's why someone with a sense of humor thought about writing ohm backwards and then wrote mo. So the unit of compliance is mo. The changes in mo that we have when talking about middle ear, the changes in compliance are so small that we have to talk in 1/1000th of a mo, which means it becomes millimo. Now I also need to introduce the frequency at which we do tympanometry. In the early days, they started using the frequency of 220 Hz. This frequency was quite randomly picked, not really random, but there was not a clinical reason for picking this frequency. It was chosen because microphones in the early days, they worked best around this frequency, so it was used for doing the measurement. What they found out later is that if you go to a frequency very close to that, 226 Hz, then something special happens for the average ear. For an average ear, the amount of millimos change with the same amount of air that is in between the probe and the eardrum. So the milliliter scale was invented, and also we started talking about an equivalent ear canal volume. So by measuring with 226 Hz, then the number in millimo at the most positive pressure is representing the volume of air between the probe and the tympanic membrane. And this only counts for an ear that behaves like an average ear, and that's why it's an equivalent ear canal volume. Basically, it became convention to say the most positive point of the curve, we call that value 0 on the compliance axis. So what happens is we move the pressure axis up to that point. And by doing so, tympanograms become a lot more comparable. Good. So let's now see if we continue a true measurement. We have moved the pressure up to the positive point, and now we're going to use the pump and pump all the way to the negative part. So here we see how a tympanogram is being measured. And now I would like to mention what happened in 4 points on this curve. And we start with the start pressure. Like I mentioned before, at the start pressure there is a big positive pressure in the ear canal, which pushes the eardrum into the middle ear, and that is why there is low compliance. Then we need to realize that per definition the pressure outside the ear is 0, that is the ambient pressure, which also means that if we look at the ambient pressure, well, in fact, in my example here, the pressure in the ear canal is now not the same as in the middle ear. In many middle ears that function completely normal, the pressure in there is slightly on the negative side. That is because the eustachian tube is not always open. It only opens when you swallow and yawn and so on. It causes that in many occasions the pressure is a little bit negative there. So the highest point of the tympanogram is in fact a little bit below 0 decapascal. And here you can see that at the highest point in the tympanogram, we have the peak compliance. We have corresponding the peak pressure, which is labeled here as the middle ear pressure, because now the tympanic membrane can move or transfer the acoustic energy at its best. And it happens when the pressure in the middle ear cavity is the same as in the ear canal. Our pump continued pumping all the way to the stop pressure, and what happens here is that the pressure is so low in the ear canal that we pull the tympanic membrane towards the probe, which means it's a very stiff cavity again, and the value dropped below the 0 line, and that is because the ear canal volume now is somewhat smaller than it was at the start pressure. So it is normally seen that the negative tail of the tympanogram will end underneath the pressure axis. Okay, so far so good. I've introduced a few measures that describe the tympanogram, peak compliance and middle ear pressure. I also would like to say something about the gradient. The gradient is describing the width of the tympanogram, and there is 3 ways that we are aware of in which people use the gradient. Now, the most commonly used one is the one that I explained first, and what you do is you take the peak compliance value, you look at half the height of that value, and there you find the width of the tympanogram. It gives you a gradient value in decapascal. Another method is that you take the peak compliance value, and then on both sides you move 50 decapascal away. With that you find the corresponding compliance values. They might not be completely the same, so you take the average of the two, and that gives you a gradient on a milliliter scale. Now, some people like to compare this milliliter gradient with the total height of the tympanogram, so they compare it to the peak compliance, and that is giving us a gradient with a percentage scale. I believe that worldwide it's most people using the gradient on the pressure scale, so half the height of the tympanogram and then looking at the width of the tympanogram. Okay, it's time to start looking at interpretation slowly. So here I bring up a true measurement that I did in preparation of this webinar. Coincidentally, we see that my peak pressure was slightly on the positive side, and it's a good time to introduce the normative box, because some people might say, oh, is that abnormal? And then I say, no, it's not abnormal because there is a normative range, and as long as the peak pressure fits within that normative range, most likely the middle ear situation is normal. Now, the reason why it was slightly on the positive side in my case is actually that the day before I came back from a trip by airplane, and apparently my middle ear pressure was still slightly different. Below the tympanogram, we also noticed that we have the couple of values. I already introduced all of them. And we have the equivalent ear canal volume on the top left, which is in the graph also represented by the bar on the right hand side of the tympanogram. Then we have the peak compliance value, we have the peak pressure value, and we have the gradient value in this case as a pressure number. When we describe a tympanogram with these numbers, and if that is how we report it in a patient journal, then we're basically doing a quantitative analysis. Now, then there is quite a few people also using Jerger's classification, and what Jerger did is that he simply said, if the peak pressure is within the normal area, then we call it a type A tympanogram. So people using Jerger's classification would not describe the tympanogram, but just write down type A. Then if the middle ear pressure is within the normal range, but the compliance is very high, so it's too easy, or it's very easy for sound to pass through the ear, then it is a type AD. It is a type AS if the pressure is within normal range, but the peak is on the low side. Then if no peak can be detected, then, or if the peak is below a very low number, you could say, then it's labeled as a type B. I also have a few other examples of type B. There is no difference in the label, but I will explain later what the different graphs mean with regard to the clinical value. And then the last type that I want to mention is type C, and that is when there is a peak, but the peak is on the negative side compared to the normal area. So that's Jerger's classification. Now it's time to start talking about the clinical value. So first I start with the tympanograms that are the type A tympanograms, and we start with the normal case in the middle. So we all expect, of course, this is a normal tympanogram. Well, I want you to be aware of that it doesn't necessarily mean that the middle ear is normal. There is situations where we know that the tympanogram can be well within normal range, but still there is a problem. And a good example of that is otosclerosis. With otosclerosis, there is a calcification of the stapes, which connects to the cochlea. And in many of those cases, you cannot measure with the tympanogram that the compliance has dropped a lot. Maybe it has dropped for this particular patient compared to how it was before, but probably it will still be within normal range. Then the top graph, where the peak is outside the graph area, actually, it means it's very high compliance. It's very easy for sound to pass through the system. Well, one cause could be that there is a floppy eardrum, a thin eardrum, maybe scar tissues due to some problems that someone might have had as a child. But if the eardrum is very thin, it doesn't result in problems. So it's not very serious if this is seen, but the peak can be very high. And on the other side, at the same time, the same graph could mean that there is a more or less serious problem. It could be that the ossicular chain is disconnected, that there is a fracture in one of the bones. And if that's the case, usually it's easily repaired with some glue, but differentiating between the two is not possible just based on such a tympanogram. They just look the same. Then for the bottom graph, we see that it's more difficult for sound to pass in through the ear. If someone has a very thick eardrum, a stiff eardrum, I wouldn't call this a too serious problem, but in that case the tympanogram can look a little bit, the peak can be somewhat low. And it could also be something quite different. The example that I mention here is that the skin of the tympanic membrane, that if it grows into the middle ear cavity and if it forms a cholesteatoma, then it can really take a lot of place, be in the way of the ossicular chain. If it's not removed, it can dissolve parts of it. It's quite a serious problem, and the tympanograms of these two cases, again, they look quite the same. Then we go over to the type B tympanograms. We start with the middle one. The middle one shows a flat line, and now we look at the bar. The bar is where the differences are, and for the middle one we see a ear canal volume which is roughly 1 milliliter. Could be my own ear actually. If you see such a flat line, it probably means that the middle ear is filled with glue or otitis media fluids. If we now look at the top line, then or the top graph, what we see is that the volume bar indicates a very high volume. It means that the air volume measured behind the probe is much bigger than we would expect from just the ear canal. So it's an indication that it's the ear volume in the ear canal as well as the air volume in the middle ear. In case a ENT doctor placed a pressure equalization tube, then this is a very healthy situation. Well, in case it is a perforation in the eardrum, then it's not such a healthy situation, and hopefully it was already noticed during otoscopy, which is of course always performed before tympanometry. Then the bottom graph. Well, we see a very, very small ear canal volume, and you might suggest that this is a measurement on a baby, and in that case, no worries, it's okay, then it would be the same as the middle situation. But if the ear canal volume is not as you expected, then be aware that this might be a faulty situation where the probe was blocked either by the walls of the ear canal, by a wrong insertion, or maybe there is ear wax that is right in front of the probe tip. So check the probe for dirt and redo the measurement would be my advice. We had the type C tympanograms left over. Here there is only one situation that I will describe. A negative pressure means that the eustachian tube function is not as good as it should be, and if the eustachian tube doesn't open regularly, then the tissues around the middle ear cavity will absorb parts of the air, and that is why the pressure in the middle ear becomes negative. Now, at the same time, fluids, liquids can build up in the middle ear cavity, and it will cause, if this remains a problem that becomes bigger and bigger, then this will over time result in a more negative pressure, and in the end it will result in a type B tympanogram. So this is typically seen in children, and that's why I also would like to pay some extra attention now to what happens if this is the case for an infant, meaning a baby between birth and let's say 4 months of age. If we present a tone to a baby ear, and if we present the 226 Hz tone, then in almost every case you will see that the tympanogram looks normal. And the reason for that is that you're not testing the middle ear properties. You're mostly testing how easy is it for sound to pass through the very flexible ear canal walls. So it's kind of forbidden to use 226 Hz on babies. If you test on babies, you need a different frequency. If you use 1000 Hz, then suddenly you're not measuring the ear canal wall properties anymore. You're measuring the eardrum and the middle ear properties. So that is a proper thing to do. Now, it could be discussed at until which age you need this. Most people agree that up to 4 months you need it. Some say up to 6. And most people agree that above 6 months you don't need it anymore. And depending on if the baby was born at full term or preterm, you might have the different age until you want to use 1000 Hz. Good. So far so good. For me it's time to do a small demonstration with Titan. I'll try to switch over to the software. I've started the Titan suite. Of course I made sure that the Tympanometry module is selected. So now I move to the left to where the protocols are. I've only made Tympanogram protocols visible. I start with the measurement with the most standard Tympanogram, which is the 226 Hz probe tone. And I'll put the probe in my right ear. And should be properly inserted now, so I'll start the measurement. Just to explain why do we have different protocols, I'll switch to the left ear, but I'll use a different protocol, which is the extended version. I'm saving my right ear data in between, and so if I do that, let's see. Okay, so we see that both my tympanograms are actually normal, but the extended protocol measures all the way up to minus 600 decapascal. The reason is that in most cases it's good enough to measure between approximately plus 200 and minus 300 decapascal. But in the case that the curve looks almost flat and you wonder, is there a negative peak which lies further out there on the negative side, then you would swap over to a protocol that uses the full range on the negative side, just to see if there is some peak being detected over there. I didn't mention before, but experience learns that if you can still find a peak, then usually it corresponds to almost no airborne gap in the audiogram. While if it is a fully flat curve, then an airborne gap is more likely to appear. And I think that for ENT doctors, this is the difference between either taking action on a shorter notice or waiting a little bit longer. So if there is still somewhat movability in the far negative region, then you would tell a patient to come back later and test again before you consider an intervention. I also would like to show you manual pump control. So I'll do that on my right ear again. I'll put the probe in the ear. I click on manual. And this is what I wanted to show to you. If you move your pressure from right to left and then back from left to right, then you will find the peak on a slightly different position. This is because the physiology of the eardrum and how it moves under pressure and when it moves is different depending on from which direction you come. That is also why it became standard to always move from positive to negative pressure, and so that everyone is doing it in the same way. If you take some older equipment, you would actually see that using the manual pressure and depending on how quickly you change the pressure, you would see that the peaks could be higher or less high, or they could move position slightly. That is because in the older system you get fewer data points per second, and also the pressure at the pressure sensor is not following the measurement as well as it does with Titan, where the pressure sensor is really close to the ear canal, so to say. Okay, I wanted to show you also 1000 Hertz tympanometry. So I select a protocol for an infant, and it's not that my ear will show the same as it shows on an infant, but maybe we will see something else interesting. And this is what I hoped for. I have on my right ear, if I measure the tympanogram with 1000 Hertz, I get 2 peaks. And now the question is, what does that mean? Well, I'm showing this to make you realize that for other frequencies than 226 Hertz, the ear is not stiffness dominated anymore. For 1000 Hertz, mass and friction have a much bigger impact, and this causes the shape to change. And in this case, it means that the highest point of the tympanogram does not correspond anymore with the middle ear pressure. Actually, the middle ear pressure is probably the same as the negative peak in between the 2 peaks. So a correct middle ear pressure would still be on the negative side. Okay, I think in practice you won't see these cases often, just because in adults it's very uncommon to test with different frequencies. Good. I came to the point of making a summary of what I have been showing to you today. I would like you to remember how a tympanogram is measured. So meaning that first the pressure is pumped to a far positive pressure, then we start the recording and we pump to a far negative pressure, and in that way we get the tympanogram. Then at the end we compare the peak pressure to a normative area, and by the shape of the tympanogram we try to make a interpretation. Now, with regards to the different diseases or pathologies that can take place in the middle ear, I think that tympanometry has proven to be a really valuable tool over the years. And I think its success is partly because of the ease in which you can do the measurement, and the ease in which a tympanogram is understood. At the same time, I hope that people can be critical enough to see that just doing tympanometry in this way, it doesn't allow you to differentiate very well between one or the other pathology. You're always dependent on other measures. Very often you have to do additional tympanometry measures like reflexes or eustachian tube function tests, or you have to look at the audiogram or even CT scans or MRI scans. The limitation of tympanometry today is that it's measured at or with one probe tone frequency, and of course with wideband tympanometry where we can measure tympanograms for frequencies up to 8,000 Hz all at the same time, then some of these limitations are solved. And it's not the topic of today, but I hope in the near future to also have a talk about that. Then we talked about the quantitative analysis and Jerger's classification. It doesn't really matter if you use one or the other. I think it depends a lot on what you have learned in school or how you're used to report things. I would like to thank you for participating in the webinar today. In 4 weeks' time, we will be back where everyone is welcome. That will be with regards to real ear-to-coupler measurements. And 6 weeks from now, we will talk about ASSR measurements. Thank you for being here today. I hope to see you next time. Bye-bye.